hopefully you've managed to get it into the form of y equals mx plus c. Normally, and we're going to do the same this time, you have the thing that you're changing on the x-axis, the thing that you're measuring on the y-axis. So we measure the time period, so we're going to have the natural log of t on the y-axis. I'm not doing the modulus lines for natural logs because I think it's clearer on the video. So the natural log of t is equal to b times the natural log of L plus the natural log of A. So this is our formula, and we're going to, I guess, try and prove this, try and find out what A and B are by plotting a graph. So in order to do that, actually, we're going to need some data. We haven't got any data yet. So now is the time when we do the experiment. You're going to want to change the length. So we're going to have a nice results table. First column, length in meters. If you started, if you started at 1 meter for your kind of longest pendulum, you're going to go down to 0.5 meters. So it's probably easiest to write 0.5 in here. I managed to go to 1.5, so I'm going to start at 1 meter. But of course, I've measured the length, haven't I, with the tape measure probably. So I know it's going to be a meter, but I know it's a more accurate than that, more significant figure. Sorry. So I'm going to put so that would be within 10 centimeters. That would be within 1 centimeter. Actually, probably the way things are, stretchy string and all that, I probably couldn't get it more accurately than that. But we're going to make sure that this column has the right number of significant figures all the way down. The time period, we're going to measure 20 lots of the time period, and we're going to do it twice. So we're going to do 20t. So this is trial 1, this is trial 2, and then we're going to have, now you could miss this column out if you want. Sorry, that should be in seconds. You could potentially miss that column out because then obviously we're going to definitely need a t average. And you can label these how you want, and that's in seconds as well. Probably the way I'm labeling it isn't best, but I'm kind of making it up as I go along. But this is these are the column headings that you want really, so you could miss that one out. And then in order for us to do our graph later on, to find out A and B, we're going to need a column that is the natural log of L. And we put our units in here. I guess I'll put the modulus lines back in. You put the units in there because it's the length that's in meters, not the natural log of the length that's in meters. And the same thing with the time period as well. We're going to want the natural log of the time period. Of course, you could have, and you quite often see actually just normal brackets here, but you can't take a log of a negative number, so we use modulus. And actually, thinking about that with positive and negatives, when you get your results, the natural log of L could be negative if you went for 0.5 meters to 1 meter. So if you've gone from 0.5 meters to 1 meter, I haven't, I've gone to 1.5. But if you have, then you're going to be doing your graph in the third quadrant. So make sure you know that when you start to draw your axes out. So anyway, we've got this, we're going to populate it with data. So I'm going to change the length, measure the time period for 20 oscillations, do a repeat, find the average, find the average time period for 1 oscillation, or just the average time period in fact, then take the natural log of L, natural log of T, plot a graph. The graph is going to be with the natural log of T on the y-axis and the natural log of L on the x-axis. I haven't put my units in, oops, what a mess. But of course, actually, your graph might, and I'll say hopefully we're going to get a straight line where the gradient is B and the intercept is A, but your graph might actually look like that. If you're in the third quadrant because you started at 0.5 meter. Okay, so once you've got your graph, then you're going to once you've got your graph, you're going to want to get the data out of it. So let's say you've got your graph, it looks like this, and this is something that hopefully you can probably do without the video really. So we're going to find the gradient will be b, the intercept will be the natural log of a, and this is a sketch if you started at 0.5 meter. Intercept will be natural log of a. Now we can find out actually from the formula that's on the formula sheet that the time period is equal to 2 pi times the square root of L over G. And so that means that if we're trying to get that into the form that we started with originally, we have 2 pi over root G times L to the power of 1/2. So B we should find is 1/2 because we're trying to link this to that. So we should find that B is 1/2. We should find that A, this intercept, if we find the intercept is the natural log of A, but we should find that A is equal to 2 pi over root G. So I'd like you to try and find out if it is or not, try and compare them. And so what I'd like you to turn in are the graph and your workings to find out A and find out B. We're comparing B to 1/2, we're comparing A to 2 pi over root G.